Yeah, it was. I mean, I don't know whether Shubro sent it to you or not, but I sent it to Shubro. Did you get it? I'm not sure how you guys access the recording. He's supposed to give it to you. Then please talk to him. Um, please talk to him. He has the video basically because I basically just provide the videos to him, and then I don't know how does he give you, like, how does he provide you the videos? Oh, he hasn't provided any of the videos. Ask him. He's gonna provide you all of them. I have provided each. I have taken two classes as far as I remember. This is the third one, so like I have provided two of the videos to him. So yeah, ask him. I'm pretty sure he's gonna give you. Anyways, this is the third video. The problem here is that uh, since you have not checked the last two videos, I don't think you will be able to understand. So the the new thing that I'm gonna start. So like I mean, can you cope up? Is it okay for you? Because I can't actually go through, I mean, I can't show you the previous content because if I show that, then I can't move on. You are understanding, right? Yeah, I have already started with organic and I've taken two classes over it basically. I have, and to be honest, there is one topic which is new, other than fairly new basically, and other than that, every other thing is same. Carbonyl, aldehydes, and ketones. You have learned this in AS, right? Actually, I showed you this, isn't it? Yeah. So tollens, failings. I taught up to this much basically. So, anyways, I taught up to oxidation of aldehydes. Uh, all right. So just check out the videos, previous videos, and note down the notes. Am I clear? You're supposed, I have provided a strict command that each time you do the class you're supposed to write them down, so the other girl who does the class with you, she tends to write the notes during the class. So I don't know which one you're comfortable with. If you want, you can check the recording and later on write the notes, or you can do in class, real time note taking. It's up to you. Is it okay? No, we won't provide you the notes printed. You will have to write them down. Like, didn't understand. Like, what do you mean by that? Oh, the whole PDF. Um, I'm not sure. It is possible. I might not. I mean, it's prohibited. Because if we do this, then it's gonna be a little bit. We have a policy. I mean, we cannot, just send it. Just send the PDF, if you know what I mean. All right. There are some PDFs we can. Huh? Sorry. I'm gonna teach the same thing, but it's just that if I release the PDF, then like the PDF will be actually the no. I know you won't send it to anyone, but actually we do. You are a good guy. What if the other student is not? If you know what I mean. Okay, fine, no problem. I'll send you the PDF. But I don't. I need to take permission from your Shubro bhai. Basically, if he provides the green signal, then I'll give you the PDF. Okay. All right. So we're gonna start the new topic: reduction of carbonyls. So what is reduction? You can guess the point: using reducing agents to reduce something out. Okay. So what is the reagent, or in other words, the reducing agent that is working out here? The reducing agent which is working out here is known as LiAlH4. I think you're familiar with it. It is known as what? It is known as lithium tetrahydroaluminate. So what does lithium tetrahydroaluminate does? It basically reduces carbonyls to alcohols. So this is an example of a carbonyl compound. What is a carbonyl compound? Something which is the functional group this, right? And there are two types of carbonyl compounds which we have seen back in our AS level and in A2 as well, the same thing, which is what? Aldehyde and ketone, isn't it? Yeah, I taught this in the previous class basically. So if you had have seen this, it would have been easier, right? Please respond because this is a live class. Because if you do not respond, then try to keep your mic on. Hello. No. This that thumbs up sign won't work because I won't. I will be working in another application, so you will have to keep your mic on to you know provide me confirmation. Okay, so propanol, and then this is the part, as you can clearly see. This thing basically comes from the reducing agent LiAlH4. Now, how does it come? You don't have to remember because it is out of our syllabus. But the thing that you have to remember is the reaction. So always remember, even though it's written provided here, but if I provided it informally, uh, this is a chart you should remember. Uh, Primary alcohol. I think you have seen this in AS, if I'm not wrong. When it is oxidized, remember, when it is oxidized, what is produced? Aldehyde, right? When we oxidize aldehyde, what do we get? Ketone, is it? Okay, now do the reverse thing. When we reduce it, we get aldehyde. When we reduce that, we get primary alcohol, right? Okay, what about secondary? What about tertiary alcohol? Actually, I made a mistake. Not tertiary, secondary alcohol. So when you oxidize secondary alcohol, what happens? You get ketone. Did I make a mistake? Exactly. No, it's okay. So when you oxidize secondary alcohol, you get ketone. If I'm not wrong, is it? Am I okay? I mean, I think it's okay. 1 minute. Yes. Oh, no. See. I told you we made a mistake here. It's not ketone here. It is carboxylic acid. Exactly. When you do that, right? That is ketone. Exactly. You cannot oxidize ketone though. Further, so that's a cross. And if you reduce our ketone here, you get your secondary alcohol back. Did you understand? Okay, so please try to remember this chart. Now, this will not be present in the PDF. I would suggest you to write it down. Have you written it down, this whole thing which I've written? Please write it down. There are some no writing which I will show during class, which you will have to write because you won't get them later on. Have you taken a whole screenshot? Okay, so try to remember this chart because this chart is very important. And then if you remember this chart, then the reactions or the examples are pretty easy. See, when you basically reduce a ketone, what is produced? A secondary alcohol, right? Which we have just seen in our chart down here. All right. Now the reducing, always remember in reduction, the reduction processes that we see down here, reduction processes, basically this one, and this one, this one, this one, and this one, these three, the reducing agent. What is the name of the reducing agent? We just saw a while ago, LiAlH4. What is the name of that? Lithium tetrahydroaluminate. Hydrido eliminate. All right, basically it provides hydrogen. All right, that's what it does. And what is the oxidizing agent in these three cases? Well, there are many oxidizing agents down there. We saw in the previous class. Even though you were not there, please check out the recordings. Please, it's a must. The first one is of course Felling's solution. The second one is of course we have Tollens reagent. Then we have, of course, K2CR2O7. I think you're familiar with that. What is the name of it? You know? Exactly. Potassium dichromate 6. And then we have the last one, which will be of course KMNO4. I think you're familiar with that as well. What is the name of it? 7. Potassium manganese 7. So these are the four oxidizing agents you're supposed to remember. And I have provided and not only that, you have to remember the colors. Color changes are important. See, the color change is different for each of the reagent provided here. All right, they basically perform the same thing, which is what is the main objective of the oxidizing agent? It is to oxidize the alcohol, isn't it, to produce the desired product. But the difference in these oxidizing agents is that different color changes are seen. For example, I discussed it earlier in the previous class that for potassium manganate 7, it is from pink to colorless, isn't it? For potassium dichromate 6, it's orange to green. For Fellings and Tollens reagent, what's it called? A little in yesterday's class, I mean previous class, I showed the observation. In case of Fellings solution, look, the blue CO2 plus ions in the solution changes to a red precipitate of CO2O. So what they're trying to say is that basically blue to red, right? From blue solution to red PPT. And if I talk about Tollens reagent, maybe it's silver mirror if I'm not wrong. A silver mirror forms exactly. So clear to silver mirror. Am I clear? Hello? Did you now the question is, where does this silver mirror comes from? It's due to basically the production of this. Okay? It is basically due to the production of silver. And why does this red PPT comes? It's due to the production of this solid. Now this is the reactions, as you can clearly see. Wait 1 minute. These are the two reactions, as you can clearly see. Do you see the reactions? See, an aldehyde is getting reacted. And what can I say? Failing solution is what? It is basically a solution consisting of CO2 plus ions. This is the thing that you need to remember about failing solution at A2 level. Even though the real reagent is very complex, but since it is out of the syllabus, I am not focusing on that. All right, so just remember that it basically acts as a source of CO2 plus ions. So here you go, you have the CO2 plus ions reacting with that, and water is water, considering it's a solution, so obviously water is going to be present. So again, we know that the color of CO2 plus is blue. It reacts to produce eventually this red precipitate down here. Did you understand why the color changes like this? This right here is in its solution form. A plus means what? It's in ionic form, isn't it? Right, that means it is in aqueous form. But when it is when it gains electrons to produce this Ag solid, that solid thingy is what? Silver in colors. That is why the solution becomes silver. So I hope you understood for Fellings and Tollens, and I don't think I have to show you for potassium dichromate 6 and KMNO4, right? Because that's, I mean, a known thing. Please write them down. Rakshit, I'm telling you again, these are not, you can take a screenshot if you want. Please, have you taken a screenshot? The ones that I write, you're supposed to write them as well, apart from the PDF. Am I clear? Okay. Okay, so that's gone. Now let's move on to the next part. Addition of hydrogen cyanide to carbonyls to form hydroxynitriles. So this is what, as the naming says it all, addition of hydrogen cyanide to carbonyls to form hydroxynitriles. So basically you're reacting a carbonyl with hydrogen cyanide, and what do we get? Hydroxynitrile. So this is the mechanism. I think you're familiar with nucleophilic addition mechanism, right? Remember nucleophilic addition reaction in AS? I have taught this in the first class, in the first two classes. I don't know whether you have not checked them out. I have provided a brief understanding of nucleophilic addition reactions. SN1, SN2. Remember SN1, SN2? Have I showed you? Exactly. These two things are new stuff. I have explained this in the first two classes. Please check them out and also write down the notes. These are very important. Now, if you cannot understand, but then if I say so, what is happening down here? You can clearly see the cyanide group from the HCN. At first, what happens? The HCN, what happens? The cyanide group basically acts as a what? Nucleophile or electrophile? Nucleophile, right? What's a nucleophile, by the way? You know that. What is it? Yeah, species which is electron rich. So will it be attracted toward like charge or unlike charge? Will it be attracted towards positively charged or negative? Positive, exactly. It's going to be attracted toward the positively charged, the partially positively charged to be exact, partially positively charged carbon atom down here, which is going to basically cause the bonded electrons present in this pi bond. We all know that in a double bond there are two types of bond. What are they? Sigma and pi, right? So in a double bond, there is a sigma and a pi bond. We will ignore the sigma bond because the pi bond is the important thing. Now, obviously, it is electron rich. The pi bond, we all know that. I think you're familiar. I don't know whether you have learned this. Actually, I teach you in S? Okay, mate. Yeah, exactly. Sorry. So I think you know how pi bonds work, right? So pi bonds look something like this, isn't it? So this is the right. You know them, right? I mean, these are orbitals, isn't it? So what is happening? These electrons basically perpendicularly overlap. Perpendicularly, perpendicularly, the electrons overlap to produce pi bond. So this is the pi bond down here. Remember, pi bonds overlap like this. Sigma bond, on the other hand, overlap like this. End on overlap, right? Remember in AS? Here? Exactly. So this is the end on overlap. And this is the sideways overlap. I think you're familiar. So again, you can clearly understand this guy down here, these electrons are gonna break down. They're not gonna overlap anymore. So as they break down, what happens? They're supposed to go somewhere, right? Who is gonna take it? The more electronegative element in the bond is gonna take it. Who is the more electronegative bond here? I mean, element here, oxygen, right? So that is what happening. He's going to take the electrons, and as a result you can clearly see one of the bond breaks down, and since it takes electrons, you can clearly see it is rich in electron. I mean, it is rich in lone pair of electron, considering oxygen is taking it down and a bond is broken. Now, since this is an unstable format, obviously you're not supposed to, oxygen does not stay like this. Since it's unstable, wherever it gets a chance to react, it's going to react. So what happens is that not all the HCN basically, dissociates to produce cyanide group. There are some HCN which do not dissociate at all. So the ones which do not dissociate at all, the bonded electrons that you see down here, it attracts the positively charged hydrogen atom towards it. Did you understand? It attracts the positively charged hydrogen atom towards it. Now, what happens in this case? This in turn is like a domino effect. This in turn causes one of the bond, I repeat, one of the bond to actually not one of the bond. Yeah, actually the whole bond basically. This causes the whole bond, the both of the bonds to break down, causing all of the bonded electrons to be taken by the cyanide group down here. Okay, so eventually, since this hydrogen atom gets attracted towards the negatively charged oxygen, it reacts, it produces a bond. You can clearly see down here. What is this group? Hydroxyl group, right? Eventually, what is produced? Hydroxyl group is produced, isn't it? Which means alcohol group, right? So eventually you get hydroxynitrile compound. So why it is called hydroxynitrile? Did you understand? We have the nitrile group down here, and we have also have the hydroxyl group down here. Did you understand the mechanism? Exactly. The next step that is important, that is the reaction of carbonyls with iodine in presence of alkali. This is another type of reaction you're supposed to remember. Please remember these reactions. See what happens. You're reacting a ketone down here, right? This is a ketone. You can clearly see a ketone reacting with iodine along with sodium hydroxide. So the conditions are pretty simple: warm very gently. The product CHI3 is a yellow crystalline precipitate with an antiseptic smell. So I think you can clearly see this one down here. What is the name of this? Do you know? Triiodomethane. What is the name? Triiodomethane. Did you understand? This is known as triiodomethane. Now this is a yellow precipitate, okay, and it has an antiseptic smell. Have you ever used Savlon antiseptic in your house? If you have used that, have you seen? Have you smelled it? Have you seen the? Have you felt the smell coming out from that bottle? Okay. I mean, okay, fine. I they're in, what's it called, Savlon antiseptic, or basically antiseptic creams or antiseptic products are very much commonly found in first aid kit box. If I'm not sure whether you've seen them or not, like for example, you know what's antiseptic, right? Huh? Yeah, exactly. Dettol, Savlon, yeah, those, yes, exactly. So, like for example, your hands, one part of your hand is cut. All right, you're bleeding. So what do we apply? We take a tissue, we soak it down on an antiseptic, and then we apply it down there, isn't it? To make sure that the bleeding stops and no amount of bacterial infection gets produced. That's the whole reason why antiseptics are used, right? It's antiseptic. Okay. Now, again, what I'm trying to say is that the triiodomethane down here, I mean, this is yellow in color, and plus, when you are found near it, you'll get to see. I mean, you'll get to smell antiseptic smell from it. I mean, an antiseptic smell will come from it, basically. Okay, so that's how it goes. Moving on to the next part. So this is the thing. Now, there is one thing you have to remember this reaction though, but the one thing that you need to remember this thing is this thing. Only carbonyls with methyl group next to the CO bond will do this reaction. That means not necessarily compounds with or this only will react. Also, this should be present as well. Meaning the methyl group should be connected with the carbonyl group. So basically, if this is there, for example, something like this, no, this will react, yes, this will react. But if it is something like this, sir, for example, CHO, sorry, H, will this react? Do you think this will react? Think about it. Will this react or not? Tell me. Yes, this will react as well. Can't you see that the carbonyl group has CH3 attached, right? Did you understand? If the compounds which have a carbonyl group with a methyl group attached, only those will undergo the iodoform test. But what if the compound is something like this? No, it won't react, right? Will it? Do we have a methyl group attached? Do we have a exactly? We don't have a methyl group attached to the carbonyl group. So as a result, this won't undergo iodoform test. What is the iodoform test? This is the iodoform test. All right. It will react with iodine to produce this thingy, the triiodomethane, yellow precipitate and antiseptic. All right. I hope you understood reactions of carbonyl with iodine in presence of alkali. The next reaction is very, yeah. Sorry. Mm, okay, fine. What's it called? Okay, can you please join after 10 minutes if you don't mind? No. Can I? I mean, can I take 10 more minutes? Then I will let you leave. Is it okay for you? Just tell your teacher 10 more minutes, not more than that. Is it a batch or like a one-to-one class? Oh, that's right. Just tell him that I'm joining after 10 minutes. I'll join at exactly after 10 minutes. All right, that's gone. The next part that we need to see is basically reaction with 2,4-dinitrophenyl So what happens in 2,4-dinitrophenyl? So the 2,4-dinitrophenyl reacts with both aldehydes and ketones. The product here is an orange precipitate. it can be used as a test for carbonyl group in a compound. Okay, so that's how it happens. So uh, the whole purpose of doing this test is what, is to identify the presence of a carbonyl group in a compound. All right, now how does the 2,4 dinitrophenyl hydrazine looks? This is the product. Do you see the 2,4 dinitrophenyl hydrazine? This is the 2,4 dinitrophenyl hydrazine. By the way, as written provided here, you don't need to learn these equations for the exam. This is just for illustration purpose. Am I clear? Okay, so what is happening here? So we have to use 2,4 dinitrophenyl hydrazine to identify whether the compound is a carbonyl compound or not. Then we can differentiate whether it's an aldehyde or a ketone. We know that there are two types of carbonyl compounds, aldehyde and ketone. Now we at first identified it is a carbonyl compound. Now, how do you distinguish whether it's an aldehyde or a ketone? We are going to use Tollens reagent. Now we'll talk about Tollens reagent later. See how it works. See, this is the example of a carbonyl compound. What is it? It's a ketone, right? I mean, it's an aldehyde, right? It is an aldehyde. So it reacts, as you can clearly see, the 2,4 dinitrophenyl hydrazine. Basically, the lone pair of electron present in the nitrogen, in the nitrile group, sorry, in the amine group, gets donated to the carbonyl group's carbon, and eventually you can see that this joins and you can clearly see this compound is produced. Now elimination of water takes place. What is elimination of water, sir? Elimination of water is that this one goes away, and also one of the H here goes away. So basically one H goes away from the nitrogen, and another and the OH goes away from here. Eventually when the the H goes away, another bond is produced. So yeah, double bond is produced and this OH goes away. So the H and the OH creates a vacuum, which in turn produces the double bond down here. Eventually this whole thing, you don't have to remember the name, the color you have to remember though. The precipitate, the final precipitate which is produced, it is orange in color. So basically if an orange precipitate is produced after you react DNP with aldehyde or ketone or any other carbonyl compounds, an orange precipitate is produced. All right, now we need to go for further distinguish process. Now how do we understand whether it's an aldehyde or a ketone? So react Tollens reagent. So reacts Tollens reagent with this. If it reacts, then it's an aldehyde. Please write them down. This is very important. Although it's not provided, you are supposed to write it down. If it does not, ketone. Did you understand? All right. So pretty cool. So that's gone. Uh, okay, so that's gone. I hope you understood. The next part that we need to check out is carboxylic acids, basically. So what is carboxylic acid? I think you're familiar with carboxylic acid. These are basically another type of functional group compounds or homologous series. Just remember one thing: the carboxylic acids are only weak acids in water, and they basically slightly dissociate, but they're very strong enough to displace carbon dioxide for carbonates. Okay, even though they're weak, basically what they're trying to say is that even though they're weak acids compared to hydrochloric or H2SO4, they are strong enough to displace carbon dioxide from carbonates. All right, so that's what I wanted to know. the solubility is very important. The solubility in water. Look, the smaller the carboxylic acids, dissolve in water in all proportions. But after this, the solubility rapidly reduces. This is because they dissolve. They dissolve because they can hydrogen bond to the water molecules. What they're trying to say is that if the hydrocarbon chain of carboxylic acid is lower, they are more prone to produce what? They're more prone to produce hydrogen bonds or to produce more number of hydrogen bonds with water molecules. And the creation of more number of hydrogen bonds leads to greater solubility of that compound, right? That's what solubility is, isn't it? Hello? Exactly. So when the chain gets bigger, for example, if I just provide you a small understanding down here, when the chain gets bigger, if I show you, so when the chain gets bigger, what happens? These are what? Alkyl, what? Electron donating groups, right? These are known as electron donating groups. Alkyl groups are electron donating groups. So instead of one, now it is receiving this bond down here is receiving what? It is receiving electrons from four other alkyl groups, right? So as a result, what is going to happen? Look, the whole thing, you have to think logically. Since the what's it called? Electron density here is increasing. Since the electron density here is increasing, what is going to happen? Uh, there is a 1 minute. What's it called? Not the bond here, sorry, not the bond. It is donating. It is donating here. Sorry, I made a mistake. It's donating to this carbon down here. So since the electron density is increasing, won't this carbon eventually become negative? Yes, it is going to become negative, and when this becomes negative, then the oxygen and the oxygen that you see in the OH part and the H part, these basically become positive in order to stabilize the whole thing, because we cannot have two negative charges together. Do you understand? So when it becomes positive, it can no longer produce what? It can no longer produce. This becomes positive, and this becomes negative, and since this becomes negative, it cannot no longer produce hydrogen bond with water molecules. Did you understand? Same thing goes for that. Do you understand? No longer produce many hydrogen. Okay, so that's why the solubility basically decreases. You can clearly see the hydrogen bonding in solid ethanoic acid. So this is known as intramolecular or intermolecular hydrogen bond. Tell me, intra or inter? This hydrogen bonding, is this intra or intermolecular? Inter. And what is this then? Between molecules. I think you made a mistake. This is intramolecular. This is intramolecular, and this is what? Intermolecular, right? So between molecules, between same molecules, this is known as intermolecular hydrogen bonding. Between two different molecules, this is known as what? Intramolecular. Am I clear? Okay, so that's it for today. I'm not taking away your time. uh when is our next class? I think our next class is tomorrow, if I'm not wrong, isn't it? Right, according to our schedule. Yeah, so next class tomorrow, we'll have more time. Today is just 35 minutes. Bye bye, see you.